She's a visiting academic in Oxford and the Chancellor of the University of Dundee in Scotland. She's been the president of the UK Royal Astronomical Society. In 2008, became the first female president of the Institute of Physics for the UK and Ireland. And in 2014, the first female president of the Royal Society of Edinburgh. She was also one of the small group of women scientists that set up the Athena SWAN scheme. And she has received many orders, most recently the $3 million Breakthrough Prize in 2018. As you can see, today's talk is going to be on pulsars and their impact on physics. I'm sure you will find this very interesting. Without further ado, Jocelyn, the floor is yours. Thank you.
Thank you. Am I heard okay?
Yeah, I think so.
Yes, good. Thank you very much. Thank you for the opportunity to be with you. I hope you're enjoying what sounds like quite hard work. And my screen, right. So I'm going to talk briefly about the discovery of pulsars, then things that they've led onto, the existence of black holes, tests of fundamental physics, and gravitational radiation. I'll keep an eye on the time. We'll see how it all goes. So radio astronomy started in the late 1940s after the World War. People who had worked in radar during the war took the radar receiving equipment and pointed it at the sky to see if they could pick up radio signals from any objects in the sky. It was already known that the sun gave out radio waves sometimes, so it wasn't totally a blind search. This particular slide shows the sun and the big radio telescope at Jodrell Bank in the north of England. This telescope has recently been given World Heritage status. I suspect it's the first radio telescope to have such status. And whilst it's a great honor, it is a big headache for the university because they have to pay money to keep it standing. Forever, maybe? I don't know. So when the early radio astronomers turned their radar receiving equipment to the sky, they picked up a lot of radio signals from different objects around the sky. And they began to wonder what these objects were. They managed to get positions for some of them and asked their colleagues, the optical astronomers, what there was at those positions. The optical astronomer said, well, looks a bit like a star, but it's not a kind of star we've ever seen before. And so these things became known as quasi-stellar radio sources, or quasar for short. What they were was a puzzle for quite a while until in Caltech, Martin Schmidt and Jesse Greenstein clicked what was happening. Martin Schmidt was looking at the spectrum, the optical spectrum of one quasar, and he was very puzzled by it. He could not find an element that would fit that spectrum until he suddenly realized it could be a hydrogen spectrum with a large redshift. He went along the corridor to where Jesse Greenstein was working on the spectrum of another quasar. Jesse was busy writing a paper trying to explain why this object should be full of tellurium, because tellurium was the only spectrum they could get to fit, even approximately. And then Martin came in and said, Jesse, could it be hydrogen with a large redshift? And Jesse tried that and found that it was. Now the snag was the large redshift. Large redshift means large velocity of recession. And in our universe, things are expanding. So there are redshifts on many objects. But the further out you go, the bigger the redshift. And because these two objects had considerable redshifts, they were clearly very distant, but they were also very bright. and this was a distinct puzzle. They had to accept that what they were finding was correct, and so the quasars became identified as some of the most distant known objects in the universe. So late 1960s, I begin to do a PhD. I have up till then worked in the north and west of the United Kingdom, places 1, 2, and 3 on this map. You can see that they're the more mountainous regions. And then, having finished my bachelor's degree in Glasgow at number 3, I go to the far south to number 4, to Cambridge, which is almost like a foreign country. It was quite scary because in Cambridge, everybody seemed very clever, quite keen to let you know they were very clever, and sublimely confident. And I felt like some country yokel, an underqualified person in Cambridge. And I was quite sure they had made a mistake admitting me. I don't know whether Portugal has comparable gradients, but I think from the perception of the south of England, this is the cultural gradient in the United Kingdom. And I have been in the land of uncouth savages, and I've now come to the area of ultimate civilization. I did feel out of place. I now recognize I was suffering what we call imposter syndrome. It goes like this. You turn up somewhere for a new job or a new course, and you recognize that everyone here is very clever, more clever than you are. You think they've made a mistake admitting you. You know they're going to discover their mistake and they'll throw me out. And in bad cases, the student will say, I'd better leave before they throw me out. And for those of us who work in prestigious places like Oxford and Cambridge, we have to look out for this, because at the beginning of the academic year, there can be some very scared new students who, if we are not careful, will run away home within the first few days and never come back. Well, I'd had a fight to get where I had got, and I wasn't going to run away, but I had to deal with this somehow. I said to myself, they have made a mistake admitting me. They will discover their mistake. They will throw me out. But until then, I will work my very hardest so that when they throw me out, I will not have a guilty conscience. I'll know I have done my best, and I just was not clever enough for Cambridge. So I was working very hard. If any of you meet this imposter syndrome at any stage in your career, I would recommend that approach. Work your very hardest, and you'll probably find you do very well, and they do not throw you out. So my particular job in Cambridge was to survey the universe for more quasars. Spent 2 years building a radio telescope, and then I alone was responsible for operating the telescope and analysing the data. At that time, the University of Cambridge had just one computer. It had memory like your laptop. It occupied a whole room because it was made not with transistors, but with vacuum tubes, what we sometimes call valves. And very few people could get time on it because it was so small, and we didn't. So the data came out on paper chart. 30 meters of paper chart every day. I scanned the sky in 4 days, so 120 meters per sky scan. And I operated that telescope for 6 months. So I had over 5 kilometers of this paper chart. I soon found lots of quasars. I also found quite a lot of radio interference. In those days, cars were badly suppressed and would give radio interference, as did things like arc welders, sparking thermostats, pirate radio stations, things like that. But in amongst the quasars and the interference, there was occasionally a signal that I could not make sense of. It took up about 5 millimeters in every 120 meters. And it appeared about once every 5 times I looked at that bit of sky. And this particular illustration shows both this strange signal and some low-level interference. If you look carefully, you can see they look different. Do you see that with the interference, the spikes go up and down, whereas with this thing, the spikes go mainly up? Here, you can see space between the spikes. Here, the spikes are so close together, you cannot see space between them. You cannot see the chart between them. When we're making this kind of comparison, we're actually doing a Fourier analysis in our heads. If, like me, you're scared of Fourier analysis, let me assure you, it sometimes works quite easily. Here, where we can see space between the spikes, we're saying that the frequencies are lower than here, where the spikes are so close together, we can't see space. So this is high frequency, this is lower frequency. Here the spikes go up and down. Here the spikes go up mainly. So we're also commenting on the amplitudes. And that is Fourier analysis, comparing the frequencies and the amplitudes. So it didn't look like interference. We couldn't really tell what it was because this was about 0.5 centimeter. So my next job was to make the chart paper flow faster under the pen so that we would get an enlargement, it would get spread out. And the thing, whatever it was, had disappeared. And of course, my supervisor reckoned that was the graduate student's fault. Everything is always the graduate student's fault. But finally, it reappeared. And this is what I got. Along the bottom are 1 second time marks. And here's the signal. And you can see pulse, pulse, pulse. One missing, but back on phase. Pulse, 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 pulse. Several missing, but little ones still in phase. It keeps the beat, whatever it is. However strong the signal, the beat is there. The label was added afterwards, and you know that, if you didn't already guess it, because of this number 1. You do not number the first thing you find number 1. It's only when you've got more than 1 that you go back and number the first one as number 1. So what is this? Well, my supervisor thought the students connected up the radio telescope wrong. But we got some colleagues who had a similar radio telescope, but a separate radio telescope and a separate receiver, and they managed to pick it up as well. So it's not that Jocelyn has wired up the radio telescope wrong, because another totally different radio telescope is seeing it. Could it be radio interference? We were very open to radio interference, but it couldn't be because this thing keeps sidereal time. You'll be aware that the night sky in summertime looks different. You see different constellations from the night sky in wintertime. That's because the stars come round every 23 hours, 56 minutes. The sidereal day is 23 hours, 56 minutes, not 24 hours. This signal, when it appeared, was keeping to the 23-hour, 56-minute day. So it wasn't Joe driving home from work in a badly suppressed car and causing interference. If it was, it would mean he was getting off work 4 minutes earlier every day, 28 minutes a week, and this has been going on for several months. That doesn't make sense. But we had a problem because the pulses were quite short, which implied the object was small, but the pulse period wasn't changing. So that implied it was big. So it's small and it's big. Aha. Then a colleague managed to get a dispersion measurement. You may not know about dispersion of radio waves, but you probably know about dispersion of light waves. When you see a rainbow or a spectrum in a dark room, you are looking at the dispersion of light into its constituent colors. Something similar happens with radio waves. When radio waves go past free electrons, the free electrons hold back the lower frequencies more than they hold back the higher frequencies. So the higher frequencies arrive first, followed by the lower frequencies. And a colleague borrowed 2 of my receivers, tuned one up in frequency, one down in frequency, and saw that the pulses came first in the higher frequency, later in the lower frequency. And by measuring the time delay and making a guess at the number of electrons in free space, he ended up with a distance of about 200 light years, which puts it way beyond the solar system, but well within our own galaxy. Now, my supervisor wondered if it could be little green men. Little green men would probably live on a planet going around their sun. And as they orbited their planet, we should see some Doppler shifts in the pulse period we pick up. Well, I found a Doppler shift, but that was due to the motion of the Earth round the sun, because Doppler shift works for the motion of the observer as well as motion of the source. We saw no evidence for motion of the source. And then just as we were beginning to run out of ideas about what to test, what questions to ask, I found a second, and then very rapidly after that, a third and a fourth. So this isn't little green men. There aren't 4 lots of little green men in different parts of the galaxy, all deciding to signal to planet Earth using broadly similar methods. This has to be some new kind of astronomical object. So following on from that, one of the consequences of the discovery that these objects, which turned out to be very small and very dense, about 10 kilometers radius and the same sort of mass as the sun, it somehow made black holes seem more likely, more plausible. And a few years later, X-ray astronomers were forced to admit that the X-ray source Cygnus X1 must contain a black hole and a relatively normal star as well. So having had pulsars, neutron stars discovered, it made black holes seem more likely. If I can get this video to run, yes, right. This is a video of how stars near the center of our galaxy move. You'll see the date in the top right, top left-hand corner. And each of these objects is a star seen in the infrared. Now, according to Newton's laws, these things should move in straight lines unless there is a force in them. There's very few straight lines. Everything is curved. There seems to be something here where there is this star shape that has huge gravitational attraction. And it turns out that in the center of our galaxy, there is a massive black hole, a mass about 4 million times the sun. So black holes followed fairly shortly on the heels of neutron stars or pulsars. It's a lovely video. You can find it online if you want to. Pulsars have been used to do a number of tests of fundamental physics. It was, I think, originally Galileo, well, it's reputedly originally Galileo, who wondered whether objects of different mass or objects of different material drop at the same speed. He was in Pisa and he was rumored to go up to the top of the Leaning Tower of Pisa and drop the objects. His contemporaries thought that these objects would drop at different speeds. But if he did the test, or wherever he did the test, he found that they all dropped at the same speed. So mass or composition did not affect the way things fell under gravity. This has been refined since the time of Galileo. When the astronauts went to the moon, they tried to do this test. The first one they did, but the video was horrible video. And subsequently it was repeated by astronaut Dave Scott with Apollo 15. And you can maybe just see a hammer and a falcon's feather. And they are dropping at the same rate in the environment of the moon, where there is rather less gas. That's actually a fairly crude system. It's also been done studying solar system bodies, and in a weak gravity environment, accurate to 1 part in 10 to the 14, objects of different mass and or different material fall at the same rate under gravity. We have recently discovered a pulsar in a triple system. The pulsar is out here, twinned with a white dwarf, and the pair are orbiting another white dwarf. White dwarfs and pulsars are made of different material, and they have different masses. So seeing how they behave as they fall under the influence of this star is an even better test of that statement about how things move under gravity. The work is still going on. There is not a large effect, we can certainly say that. So they're having to do very careful study of errors, experimental uncertainties. One feature is if the gravity of the central object affects these two objects differently, then their orbit will become elliptical, orientated towards the central object. So that's work still ongoing. Initial results say no effect. They behave the same way, but I think they're still continuing to try and get a better answer. So I think I've probably said that if the pulsar and its companion fall at different rates, their binary orbit will change and the eccentricity will point towards the external field, which in this case is the star at the center. There's been other ways of testing Einstein's theories. There's now quite an industry testing Einstein's theories. The first one was back in 1974, when Hulse and Taylor discovered the first pulsar in a binary system. Joe Taylor was working at Massachusetts University. Russell Hulse was his graduate student. Russell Hulse got banished, poor lad, to the Caribbean, to Puerto Rico, where there was the big Arecibo radio telescope. That radio telescope has recently collapsed, so which is sad, but this is way back in 1974. And Russell's job was to find new pulsars, and he found lots, but there was one he was having trouble with because its period seemed to keep changing. And they ended up deducing that this pulsar was twinned with another star. It was a binary pulsar. The other star was a neutron, another neutron star. And as these two objects orbited each other, the orbit was gradually shrinking by about 7 millimeters a day because there was gravitational radiation coming from this system. People knew about gravitational radiation, but this was the first suggestion that the theory might be right. The theory was very right. They managed to show that the way the orbit decayed was consistent with general relativity to about 0.3%. They subsequently discovered another binary system where both objects are pulsars. So it's a double pulsar. And they've been using that to test general relativity. The best published figure I can find is from 2015, when they showed that GR was good to 0.02%, which is pretty good. Sorry, my system's frozen temporarily. Okay. So this double pulsar, two pulsars orbiting each other, an orbital period of about 2.5 hours, which means they would both fit within the sun's diameter, the sun's size. It's a very tiny orbit. And we're lucky in that the orbital plane is nearly edge on. So we see one pulsar eclipsing the other, or at least eclipsing the magnetosphere of the other. And yep, I've already given you this figure for how good GR is. I don't think I need to add anything from this slide. Artist's impression of what they look like, but that's okay. So far, Einstein's theories have stood up to all the tests that we can throw at it. The pulsar astronomers are continuing to use pulsars to test general relativity. There are some issues with general relativity, as you may know. Singularities, and also meshing general relativity with quantum physics. So there is a suspicion that at some level, general relativity has problems, which is why the pulsar astronomers keep attacking it. Another consequence of general relativity, which again, pulsars, neutron stars, have made more realistic, is gravitational radiation. If you put a heavy weight on a mattress on a bed, the mattress bows. So this might be your mattress and this is the heavy weight, and there is a dip. Can you imagine moving the weight up and down? Then the shape of this bow keeps changing, and ripples go out through the mattress, little ripples radiating out. Same sort of thing happens in space. Massive objects distort space, bend space like that. And if these massive objects move, you can get ripples in space-time radiating out from the moving object. This is called gravitational radiation. This is a mock-up from Wikipedia. It's a lot clearer than it is in real life. There's a pair of neutron stars in here going around each other, and they are making waves in space-time, and the waves radiate out at the speed of light. Alas, they are not actually that clear, but after many decades of trying, gravitational wave astronomers have found gravitational waves. What you expect is, I've got these two objects orbiting each other, and as they lose energy to gravitational radiation, they move closer. So here's the wave. The frequency is getting higher because the two objects are getting closer, and the amplitude is getting bigger because the two objects are getting closer, and there's more and more gravitational radiation until ultimately the two objects merge, collide, and form one body. The technique they use for detecting these gravitational waves is based on the laser interferometer, which has two arms at right angles. As a gravitational wave comes by, this arm will lengthen, this arm will shorten. then the first arm will shorten and the second arm will lengthen. And so using this Michelson-Morley type of interferometer is absolutely ideal. The only snag is the movements are very, very small, so it's really hard to detect. And it's taken probably about 50 years of development until they managed to achieve the sensitivity to make a detection 5 or 6 years ago. The movement of the light fringe is very, very small. So if you have 4-kilometer long arms, which is really big interferometer, lots of technical issues there, but if you have 4 kilometers, you would look for a movement of about 10 to the minus 18 of a meter, which is comparable with the size of an electron or a quark. So you're dealing with very, very small signals, a strain of 10 to the minus 21. The luminosities, the energy dumped into space, can be 10 to the power 50, 10 to the power 52 watts. But space is very stiff, and you end up with these tiny, tiny movements. But they have done it, and now we are steadily opening up the gravitational wave spectrum. So we have a whole new way of viewing gravitation, of viewing space through gravitational radiation as well. This is the famous signal from 2015, September the 14th, when they made the first particular detection. They're using 2 detectors, and to begin with, you see there's not much agreement, but then they come into sync. The amplitude is getting bigger, the frequency is getting higher, goes wham, 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 and then they merge and it goes relatively quiet. This wasn't the merger of neutron stars. This turned out to be the merger of 2 black holes, each about 30 times the mass of the sun. Until then, we didn't know such black holes were common. But since then, LIGO has detected a number of mergers, and they're nearly all black holes. And they're nearly all something between about 20 and 100 solar mass black holes. Very few neutron stars, I regret to say, but they'll get more. But they got the first merger of 2 neutron stars in August 2017. And it wasn't a very strong gravitational wave, but there was a gravitational wave which LIGO detected and announced. And the gamma ray astronomers said, oh, we saw a short gamma ray burst just 2 seconds later. The gamma ray astronomers were able to reduce the error bar. The LIGO error bar was about, I don't know, a quarter of the sky. The gamma ray one was a good deal smaller. It still contained a lot of galaxies, but they were able to spot a change in optical brightness on the margins of a particular galaxy on the same sort of time scale. So putting together the gamma ray, the optical, and the gravitational wave, they've picked up what this is, and it's turned out to be the first merger of 2 neutron stars, as opposed to black hole mergers. I think I will stop there, give time for questions and so on, if that's okay with you.
Yes, if you want to, you still have another 10 minutes or so to go. I can, if you want to continue. If not, we can stop for questions.
I think maybe a chance for questions would be good.
Okay. Then I ask any of the participants if they have any questions they want to ask our speaker. Just raise your hand, write them in the chat, and I'll allow you to turn on your microphone and your camera. Everyone's being quite shy. If not, I can ask one quick question. Okay. Not a question. So Ali, let me find you. You should be able to turn on your camera now, so you can ask your question. If not, I'll read it on your behalf. So Ali asks, what are the future plans for this field of research?
Thank you. The work is carrying on. There's a number of things you can use neutron stars for. I've mentioned some of the tests of GR, for example, so that work is continuing. You can also use them to study the space between the pulsar and the solar system. And it turns out that there's plasma there, material there, which is not uniform. And so there's quite a bit of study of that. Why is the interstellar medium a bit clumpy, and what is it doing, and why? There's also a lot of work trying to understand the mechanism that produces the radio beam. The pulsars work because they produce a beam of radio waves, and as they spin, the beam will sweep across the Earth and we'll pick up a signal. So it's a bit like a lighthouse. You see it when the beam shines on you. What is actually producing the radio emission, how it's produced, is a tricky subject, partly because the conditions are so extreme. It's an enormous magnetic field, enormous electric field, general relativity matters. There's so many extremes all at once that it's actually pretty hard work. There's also work going on to study the insides of these objects. They have a radius of about 10 kilometers and a mass like the mass of the sun. So they've got very high density. And then the question is, what is the inside of the object like? And there's enormous debate about that at the moment. It's quite hard to get a reliable, to get good data on it, to get useful data on it. So there are quite a few models around, but the physics is extremely extreme, shall we say. So a lot of interesting physics there, particularly towards the center of the objects. I think there's a lot more physics advances to come.
Thank you. I think we have another question from Joanna. So if you want, you should be able to turn on your microphone right now. Oh, perfect.
Hello, good morning. Can you hear me? Okay.
Yeah.
Yes.
My question is just to see if I'm understanding it a bit. So if we study two bodies, gravitational waves, if you study their wavelength and their amplitude, we can check whether they are in the verge of collapsing?
Yes. What the frequency of the wave, no, I need to go back. We're dealing with objects in a binary system, two objects orbiting, and the frequency is the orbital frequency. And as they get closer, they go round faster and faster and faster until they merge. So by studying the frequency of the wave, you can see the frequency of the orbital motion. And you can also get the separation of the two objects. You can see how far apart they are as they merge. Does that answer your question?
Can't hear you, but I think so. Yep. Seem to be having some technical issues. In any case, so we have another question from Owen. I think you should be able to turn on your camera now if you want. Yeah.
Yes. Yeah, so Professor, you mentioned the Arecibo telescope in Puerto Rico a little earlier, and I was also thinking about that as you were speaking. I was wondering, it's quite topical now, what kind of facilities are seen as necessary for radio astronomers for developing the field into the future? Do they want a replacement or similar sort of instrument to the Arecibo telescope, or are different instruments that are being built, like the Square Kilometre Array, more useful for what radio astronomers are looking for now?
The Arecibo telescope was particularly good for finding new pulsars, for surveying the sky at depth, in other words. But there are, as you say, a lot of new radio telescopes coming along. There's the telescope that's building partly in Australia, partly in South Africa, the Square Kilometre Array. That's probably the biggest one that's coming along. But there's also a major low frequency telescope that's been operating for a few years, which is right across Europe, all the way from Poland to Ireland, and from Scandinavia to Pico Veleta in Spain. So there's several new radio telescopes coming along at different frequencies. The other ones that's happened quite recently, there's a big one in Canada called CHIME that's doing interesting work on a slightly different topic. One of the accidental discoveries by pulsar astronomers was that every so often you can get a very strong single pulse from a phenomenal distance, very high redshift. These pulses look a bit like a single pulsar pulse, which is how they were discovered, but the dispersion on the pulse shows that it has to be way beyond our galaxy and in some other galaxy. These things are called fast radio bursts. And pulsar astronomers are also studying fast radio bursts because they're very sexy at the moment. They're big puzzle, very intriguing, very strong, at least strong at the source, but also way, way beyond our galaxy. Whereas we haven't yet found a pulsar outside. Well, we found pulsars in the Large and Small Magellanic Clouds, but there are satellite galaxies. We haven't found truly extragalactic pulsars yet. So there's a lot going on, as always, and continuing improvement in the telescopes available as well, which is great.
Okay, great, thank you. We have another question from Imanshu. So if you want, you should be able to turn on your camera now. Yeah, perfect.
Hi, Jocelyn. It was a very nice lecture.
Thank you.
I wanted to know, as for increasing the internet speeds and all these monitoring purposes, we are launching multiple satellites and multiple countries are launching them. So launching of these many satellites, will it cause any effect to the studies which are being carried out about the objects in the solar space and the galaxies?
Yes, the big worry at the moment are the big constellations of satellites to give good internet coverage, fast internet coverage. And that will hugely affect astronomers at optical wavelengths, the conventional astronomy. That is a very, very big worry at the moment, and I don't know how it's going to be sorted out. There's also competition for bandwidths in the electromagnetic radio spectrum. Telecommunications want more bandwidth, please. And radio astronomers are having to fight quite hard to keep the bandwidth that's been allocated to them, to keep it clear. It's partly a case of stopping stray signals from internet providers and mobile phone providers. It is worrying, the electromagnetic spectrum is under a lot of pressure now. So both at radio and at optical, there are big worries. Yeah.
Thank you. We have another question from Alec.
Good morning.
Good morning.
So my question is from the last slide, I guess. So isn't it a bit mysterious to have 2 seconds later the radiation after seeing the event from a 130 million light years away signal?
Well, the two are very closely linked. The merger happens and then the gamma ray burst comes just 2 seconds later. In one sense, we're lucky that it's only 2 seconds. If it had come a day later, it would not have been so clear that it was connected with the gravitational wave event. So the 2 second delay is okay. We're pretty certain it's the same thing. And then you see the optical brightening as well. So does that answer your question, Alec?
Not sure. I think it does. I'm not sure if he can turn on his microphone right now because
Well, I can hear you, so that's okay. It's good.
oh, okay. But yeah, I assume it answered Alex's question. If not, just write in the chat and I'll give you. You'll be able to turn on your microphone again. We have another question from Imanshu. So let me find you. So just a second. There we go.
So ma'am, I have one more question continuing to that question. That these bandwidths are affecting us, and as you said that the electromagnetic spectrum is under a lot of pressure. Is it possible to carry?
I can't hear you, Himanshu, because there's background noise. Could you try again?
Just a second, just a minute. Yeah. I was saying that as you said, there is a lot of pressure on the electromagnetic spectrum at present. So can we carry out these astronomical studies through spacecraft, like collecting the signals from the outer space within the spacecrafts which are being launched, satellites which are being launched in the space, in our Earth's orbit? Is it a possible solution?
Yes, it is possible. The satellites we are launching get better and better with each generation of satellite, so we can do more and more. And we can also put, for instance, X-ray telescopes on the space station. So at the moment, one of the important sources of data is a package called NewStar on the International Space Station. It works in the X-rays mainly, but there's a lot of useful information that it's giving us. And more, we all have to work at different wavelengths. So you cannot simply be a radio astronomer or simply be an X-ray astronomer. You have to be able to work with data from both and understand the meaning of the data from both. So we become much more multi-wavelength.
Thank you, ma'am.
Okay, great. We have another question from Devyansh, which, if I understand correctly, is if you would like to be involved with a project, another project that won a Nobel Prize. But I'll allow them to turn on their camera if they want.
Good morning, Professor.
Hello.
Would you like to win another Nobel Prize?
I have done very well for prizes, actually. And one of the advantages of not getting a Nobel Prize is you get many, many other prizes.
Okay.
But if you get a Nobel Prize, other people say, we cannot match that. Our prize is not so good. So you don't get other prizes. You have this one event, the Nobel Prize, and nothing else. If you do not get a Nobel Prize, you get many other prizes. So each year there is a party, much better.
Thank you so much.
That's great. Are there any more questions? Does anyone else want to? We still have a few minutes left. If not, in the meantime, I'll ask my own. It's a bit of a more generic question. Right at the beginning of your talk, you talked a little bit about your career and sort of your path from PhD onto academia. Most of our participants right now will be undergraduate students, second, third year, master students. So I'm sure a significant percentage of them currently debating whether or not to pursue a PhD, whether or not a career in research is for them. I was just wondering if you wanted to quickly comment. We all know the unique set of challenges academia can pose. Essentially, if you want just to quickly comment, what kind of advice would you give to aspiring young researchers maybe about to embark on a PhD journey?
Yeah, I think if you think you might like research and you can get a place to do a PhD, a doctorate, then I'd say go for it. That will help you decide whether you want to stay in academia or whether you want away from universities and out into the real world, the big wide world. Having a PhD will not prevent you getting a good job outside of a university. And it does give you the chance to try doing some research for a bit and see whether you like it and how you get on. So if you can get a PhD place, working with somebody you think will be okay, and it's an area of science that you're interested in, then I would say go for it. Give it a try.
Yeah. Thank you. Yeah, definitely. Okay, we have a question from Georgia. Should be able to turn on your camera now if you want to. I'll just read the question then. So Georgia asks, thank you for the wonderful presentation. Could I please ask if you have observed cultural change in research and what you might be expecting or hoping for in the future?
I missed a word near the beginning of that, I think, Pedro.
Could I please ask if you have observed a cultural change? I'm guessing a cultural change in research and academia, and if so, what you might be expecting or hoping to see happening in the future.
Yeah, thank you. I like that question. One of the things I've done quite a lot in my life is to work to make it easier for young women, as opposed to young men, to be able to have a career in academia, have a good career. In astrophysics, we get more female PhD students than the rest of physics. So astrophysics is seen as more women-friendly than the rest of physics. But women are still in a minority. It might be 1/3 women, 2/3 men at the moment. It's gradually evening up, but not there yet. It's generally become the case that as there are more women, departments become more women friendly. So it gets better in that sense as well. So people are more alert to subtle gender discrimination. We have, excuse me, we still haven't really become properly alert to subtle racial issues, but we're working on that. We're getting better there. But certainly for women, the situation has improved hugely over the last 10, 20 years and is improving all the time. And so I can encourage young women to stay in science, maybe even do science research.
Okay, thank you. Are there any more questions? Okay, Barbara has one. Let me find you.
Hello, can you hear me?
Yes, thank you, Barbara, I can.
Thank you for your nice talk. So I was wondering if for those who study astrophysics, is there any other kind of job besides researching that those students can follow?
If you do astrophysics, you get a very good physics training, and you can move sideways with that physics training. If you want to do astrophysics itself, it really means staying in universities or observatories. There's no other way to do astrophysics, but the physics you learn is very widely applicable. You can use it in many ways and in many places. And you also learn other skills, not only how to manage your own time and how to work in a group, but you may also have responsibility for a project. So you have management responsibilities as well. You learn many, many things through doing research. And actually, the one thing that's most difficult to do is how to recognize what you have learnt and be able to say, I have experience of managing a budget or managing people or developing computer algorithms or all sorts of whatever. But what you learn can be used very, very widely.
Okay, thank you very much.
Thank you.
Thank you. Any more questions? If not, we're right on time. Thank you again, Jocelyn, for what was a very great and interesting talk, not just on the research side of things, but I think on the human side of academia is also very important. And thank you again for having accepted our invitation to be here. I'm sure all our participants will have enjoyed this as much as I did. So thank you.
Thank you all, and have a good day and keep safe.
Thank you. Bye.
Bye-bye.